Let's establish whether this series is convergent or divergent. First, we see the denominator approaches infinity as n goes to infinity. So 1 over n ln of n approaches 0. The test for divergence does not apply. Let's use another test. Well, this looks like we could use the integral test, because we could do a substitution, u equals logarithm of n, and that's going to work. So let's try to apply that. So that's my an. I need to use a function. So consider the following function, so that when you plug n for x, you get exactly an. Now we need to check some assumptions on f. So first of all, f continues. So definitely this is true for all values when the denominator is not 0. X is 0 at 0. Logarithm of x is 0 when x is equal to 1. So for sure, for x greater than 1, the function is continuous. In particular, here we're even starting at 2. So it continues for x greater than or equal to 2. Yes. Check. Then positive. Well, for x greater than 2, yes, this function is going to be positive because x and ln of x are going to be positive. So that's also a check. And then f decreasing. So you could check this by either taking the derivative and showing that it is negative, at least in this range of values for x. But we could do something quicker here. So we know that x and ln of x are increasing functions. So x times ln of x is an increasing function. And if I take the reciprocal of an increasing function, that's going to be a decreasing function. Therefore, this is also a check. Now we have checked all the hypotheses. I don't need them anymore. I know that I can apply the integral test, so I'm going to erase them. And now I'm going to compute the improper integral. Like this. Remember, the improper integral is to be understood through a limit. So let's say limit when m goes to positive infinity, integral from 2 to m. Clearly this is improper only at infinity because we already observed that the denominator is 0 at 0 and 1, but here we're starting at 2. Okay, great. So now let's do a substitution. We could do u equals ln of x. So that du is 1 over x dx, which is exactly what we have here. So this will become 1 over u, and then dx over x will become du. So this is 1 over u du. Remember, this is a definite integral, so we need to change the bounds as well if you want to be correct. So when x is equal to m, then u is equal to ln of m. And this bound, when x is equal to 2, then u is equal to ln of 2. Okay, great. Now let's just compute the integral. That's ln of u, evaluated between ln of m and ln of 2. So this means I need to compute the following limit, right? First I evaluate at ln of m, and then I subtract, evaluate at ln of 2. Now I have to take the limit when m goes to infinity. So m is only here, so this is gonna, the limit is gonna be here. Now, ln of m approaches infinity when m approaches infinity. And therefore ln of m will also approach infinity. So this goes to infinity, and logarithm of something that approaches infinity is also infinity. So this limit just turns out to be positive infinity, which means the improper integral is divergent, and by the integral test, our series is also divergent. So divergent by integral test.